Hi to those that are joining. We are going to give it just a minute before we get started with today's content. Okay. Hey everyone, thank you for joining today's webinar with Energy Solutions. Today we will be discussing their project, Grid Connected Heat Pump Water Heater Benefits for Low-Income Households in the Southeast. We're very excited to be partnering with Energy Solutions, who will be sharing about their Grid Connected Heat Pump Water Heater pilot. While folks are still joining us, I just wanted to go over a couple of the housekeeping details. Please note that the webinar is being recorded and will be shared to all the registrants after today's call. Additionally, if you have any notes, we hope you have a bunch, please put them in the Q&A box and some of our speakers will be able to get to them throughout the presentation, or we'll just hold them off towards the end. Additionally, all of our speakers are going to have their emails at the end of today's presentation, and we would love for you to reach out and see where you could possibly collaborate in the future. So please don't hold back. And then finally, I've got to, of course, make the plug. Coming up in just a few short weeks is this year's Southeast Energy Summit, based here in Atlanta, Georgia, where SEIA is headquartered. It is from November 17th through the 19th. That's a Monday through Wednesday. And yeah, we would love for you to scan the link to register and join us, as well as other organizations and folks vested in this space, continue to discuss topics like these. So without further ado, I would like to introduce today's speaker in order of their presentations. To start, I've got Claire Williamson. Claire is a senior energy policy advocate at the North Carolina Justice Center. It's also referred to as NCGAC. She advocates for safe and affordable energy policies for low-income North Carolinians. Prior to joining the NCJC in 2020, she worked for the DC Sustainable Energy Utility. Oh, excuse me. One moment, please. Implementing energy efficiency and renewable energy programs for residents of the District of Columbia. Helen is a senior project manager in the Policy and Ratings Department. Helen has a broad background, including 5 years at HRI, a year on Capitol Hill, and 10 years as a civil engineering consultant. At Energy Solutions, Helen contributes to appliance standards and building code efforts in California and New York. She focuses mainly on water heating, but also covers commercial food service, plumbing fixtures, and a variety of other products. Daniela is a senior staff engineer at Energy Solutions, focusing on demand management for distributed energy resources and appliance standards. At Energy Solutions, her key responsibilities include technical leadership on utility demand management programs, technical assessments of demand management related controls for automated demand response programs, and technical strategy for smart technology load shifting programs. Okay. Now that I am done with my script, I will turn it over to Claire to kick us off.
All right, good afternoon. Thanks for being on, everybody. So the North Carolina Justice Center, we're a nonprofit advocacy, anti-poverty advocacy organization. And we were really excited to work with Energy Solutions on a connected heat pump water heater project that's targeting and studying savings for harder to reach and low income communities. So just to give you some perspective in the space about the Southeast, you can go to the next slide, Daniela. And the next slide. We'll talk about the project motivation and kind of background. That's what I'm here to share about, which is, first of all, the Southeast has a high penetration of residential electric water heaters already. So considering and thinking about switching them to heat pump is a little bit easier to make that conversion, and there's more potential for that market uptake. And there are programs in the Southeast that have demand response programs as well. So there is this seemed like a good area, and we were excited to kind of be the host site for this study. Looking at demand, not just energy savings, but demand savings for heat pump water heaters, there were a couple of studies. You can go to the next slide as well, Daniela. There were a couple of studies that have happened before. Really, there's like two, one from 2018, where the Pacific Northwest National Laboratory did a pretty large scale connected heat pump water heater. And then there was one in Florida as well in like 2022 that did both the lab and then the field testing. And so we wanted to do like field testing specifically focused on like low income, kind of harder to reach participants, to understand what are the barriers to making this could be, a large potential of demand savings, and what would it take to have a program like that. So you can go to the next slide. The idea for this program started with my project director, Al Ripley, talking to Chris Granda, who's at the Energy Solutions like years ago, at a conference. And a couple of things came together to make it possible. One factor in place is that the Justice Center had been working with a network of home repair and housing agencies in our local community in Orange County, which is in central North Carolina. And there was a great organization, and they're now called Preserving Home. At the time, they were known as Rebuilding Together of the Triangle. And they ran a collaborative where people got homes basically weatherization ready. So we had some connections for people who do that work. Also, this program really got started when during COVID, there was, some of the recovery dollars, and the state energy office in North Carolina was like, how do we spend large amounts of money fast that's going to have energy savings? They really wanted to have like energy efficiency, energy savings. And we pitched them on the idea of directly paying for heat pump water heater, like direct installs. So we got the funding for the purchase of the equipment in people's homes and could provide these heat pump water heaters to households at no cost to them. So that was really, really important. But the like cool study part of it also came together from several different places where there was the Department of Energy provided in-kind services of like the monitoring devices, the EcoPort communication modules, and they did also some of the analysis, the Pacific Northwest laboratories, and Daniela came out, and Energy Solutions provided, that we've got some private foundation funding to do the actual creating demand management. You'll see all this detail here in a second, but several of these factors came together so we could not only provide this more energy efficient equipment, but also really answer some and learn some more about what's it like to install these, but also what are the savings, what are the demand management issues, what are the challenges. So you'll see all that in the upcoming part of the presentation. Do you want to take it, Daniela or Helen?
Yes, I can. I'm going to cover the next section of slides, talking about just kind of facts about our participants and getting the project going. You go ahead to the next one. So this slide is a little bit about Energy Solutions, where Danielle and I both work. We're mostly a program implementation consultant through our DERS and EE departments, but we do a lot more through policy and ratings departments, where we work on codes and standards advocacy. And then we have our business strategy department that works on emerging technology projects. So we're really like running the full, energy efficiency in all the spaces. This project was done through our policy and ratings department, which is where I work. Daniela is in our DERS department, so is an expert on the distributed energy resources that were used. You can go to the next slide. So there were three main goals for this project. The first being we wanted to save energy and money for our participants through the use of load shifting on a time of use rate. This is particularly obviously important for the low income population, and it's worth noting our participants were not on a time of use rate. We didn't have control over the other electrical equipment in their homes or any insight there. So for the study, we calculated what the savings could have been if they were on a time of use rate. So in the future, maybe that's something that will make sense. Then our second goal was to demonstrate that the load could be shifted, the water heating load could be shifted off peak times without participants noticing loss of hot water. So operating within their load profile and also better understanding what this population's load profile looks like for program design in the future. And then lastly, we wanted to learn more about what it takes to initiate and maintain a load shifting program for a low income population. You know, how do we get the word out? How do we get people signed up? Next slide. Here's this is showing the key facts from our study. We had 24 homes participate. They all had e-radio eco-ports using the CTA 2045 messaging that were installed and operating for 1 year. There were no mixing valves installed, so there was no changes to the participants' water heater operating modes, that we left them as they were. All the participants were single family, low income homes. The participants were paid $200 in total, 100 at the beginning after completing an initial survey and getting everything installed and working, and then 100 at the end after doing a mid-study survey and a final survey. Next slide. So we had a very diverse set of homes, as you can see here. The size and the year built was a large range. The water heaters were also installed in a range of conditioned versus unconditioned spaces. So sometimes in an unconditioned garage, sometimes in an unconditioned basement, that's kind of a semi-conditioned space, and then several within the home in a closet or in a laundry room. So we were also surprised that about half the homes had gas water heaters prior to the study. As Claire noted, most of this area has a lot of electric water heating, so we expected more of that, but it was cool to be part of some fuel switching there. We had almost all 50-gallon tanks, one 80-gallon tank. And the water heaters were installed by formally rebuilding together the triangle over a 2-year period. So from mid 2021, then we started the study in mid 2023, and some participants had just received their water heater, others had had it for a couple of years, so had seen some bill savings and that kind of thing. Next slide. All the occupants were mostly seniors and adults. There was only 5 homes that had teenagers or younger. They were all low income, with about 80% being considered very low income, so below 50% of the area median income. So you can see the breakdown on the slide of the number of occupants. 20 of the 24 homes only had 1 or 2 people living there, so pretty low usage, which makes it easier to shift the load. It's throughout the year that we were monitoring, there were several of the homes that had a change in occupancy, which supports the need to oversize, make sure you're sizing correctly, because the occupancy can change, and increasing occupancy can really hinder the ability to load shift without impacting the hot water supply. So next slide. So this is kind of the highlights of recruiting. This is my last slide before I'm going to hand it over to Daniela to talk about the actual data. So preserving home was really well known. They had provided free heat pump water heaters to this pool of folks that we reached out to participate in the study. and everyone was really happy with them. Many of the participants had seen a bill savings. So the recruiting was a little definitely easier with that warm intro, much easier than it would have been for cold calling these homes. But there was definitely challenges because many of the occupants didn't regularly use their email. Some didn't have Wi-Fi. So there was a lot of phone calls had to be made, and like remind you working with sometimes grandparents or grandchildren or children to help get the paperwork signed through email. Um, some participants didn't have a voicemail set up, so that was a challenge to get a hold of them. They were, and then once were up and running, we had some issues with, participants couldn't always help us troubleshoot if the connection was lost for some reason. They couldn't always see the controls or the UCM, the light on it. So that was a bit of a challenge as well. And we had hoped to use the manufacturer's cloud as sort of a second check for the e-radio modules, but most participants were not willing to download the app. They didn't trust that kind of online interaction. Some of them didn't have smartphones. So we were only able to do that for a couple, and it wasn't as useful as we thought it could be. So we did learn a lot through this study about the best practices of reaching this population. Definitely mail is going to be a thing still, and it's just not as quick as it can be with the more younger population that's constantly on phones and email. So Danielle is going to talk about the load shifting design and results.
Yeah, all right. Yeah, thanks, Helen. Yeah,
Thank
so
you.
I'm gonna talk about some of the results from the study. As Helen mentioned, one of the goals was to demonstrate how the demand management features of these connected water heaters can provide additional benefits for low-income customers and the grid in the Southeast. And this would be in addition to those energy efficiency savings that customers would get from switching from a standard electric water heater, for example, to a heat pump water heater. So yeah, this section is about how we design the load shifting aspect of this study to achieve some of those goals and what we learned. And if you're not familiar with the term load shifting, that just means shifting a customer's energy demand or load from one part of the day to another part of the day when electricity is cheaper or when there are more electricity resources available on the grid. So this slide shows the territory and some of the information about the utilities for the participants in the study. So for participants to save money by load shifting or moving their energy use around, they have to have access to an electricity rate that incentivizes that behavior, such as a time of use or TOU rate, where electricity is cheaper during off-peak periods compared to higher prices during the peak period. So the first thing we looked at when designing this study were the regional time of use rates available to our participants, with the goal of developing a shifting schedule that would shift energy use to the off-peak periods that are cheaper for the customers. So 60% of the study households were Duke Energy customers. They were pretty evenly split between Duke Energy Progress and Duke Energy Carolinas. And so the utility territory that we're looking at is the one highlighted in the box in the image on the right. And at the time the study was designed in early 2023, most of the participants did actually have access to a time of use rate. But as Helen touched on earlier, for the purposes of this study, we didn't ask the participants to change their rate schedule because we were only controlling the water heater and not any of the other appliances in their home that they might not have been able to shift around. So we didn't want to create any negative impacts for them. So we did calculate the cost impacts for the water heater operation if they had been on a time of use rate, but again, didn't actually have them make that change. So here's more detail on some of the Duke Energy time of use rates that we looked at as a starting point to decide when to do the load shifting for this study. And this table shows those rates that were available at the time the study was designed in early 2023. And the top table has the winter rates, the bottom table has the summer rates. The peak periods times are shown in red, the shoulder periods are in pink, and off-peak is white. So, the red is the most expensive times of the day, and the white is the cheapest times of the day. And as you can see, there's lots of rates, and the peak periods do differ actually across the rate options. So we looked at what the most basic rate that would be applicable to our participants would be, and that was the one called RTOU 79. So that's the second row in both of these tables. And for that rate, there's a really long peak and shoulder period. It's about 9 hours a day of higher prices in both winter and summer. And it is challenging to reduce the energy demand for such a long period of time for water heating, because that would mean that you have to hold off heating water for that time period. And if you have a lot of hot water use, you might have to recover the heating at some point in that window. But as mentioned, the majority of our participants were seniors with only 1 to 2 occupants per household. And because of their overall small and infrequent water use, they were a little bit more flexible about when they would need to heat water compared to some of the other, what other demographics would have. And, they just didn't have to heat water that often, which was an interesting finding of this study. So that actually made this demographic uniquely well suited to defer their water heating for a long period of time in alignment with these peak periods. So that said, based on these different schedules, we chose to schedule the daily load or demand reductions from 6 a.m. to 12 p.m. and 4 p.m. to 9 p.m. in the winter and 1 p.m. to 9 p.m. in the summer. And so those are just aligning with some of these high price periods. So that's when we want to reduce the energy use. And that captures the time windows that the participants would be asked to reduce if they did sign up for one of these time of use rates. So to summarize that, here are the actual schedules that we used and the signals that we use in the study for shifting around the participant energy use. So to design these schedules, as mentioned, we looked at the time of use rates in the region. And in addition to those, we looked at some of the seasonal differences. We looked at results from prior studies like the PNNL studies that were mentioned earlier. And we made some simplifications as well. So for example, Duke Energy Progress in Carolinas had a slightly different definition of the summer versus winter months. We decided to use the same definitions for all of the participants to keep them all on the same schedule and collect the most robust data. So even though all of the participants were, on some of the different rates, we kept everybody on one schedule. So we had our summer season as May through September, and the winter season as October through April. And then we split those into a, cold and shoulder for the winter, hot and shoulder for the summer, to kind of differentiate the results a little more. We also use the findings from the PNNL, heat pump water heater load shifting studies, to inform the length of the signals, the strategies for different weather conditions, and the specific signals that were used for load shifting. So with all of this information, all of that was synthesized to create these schedules shown here. So there's 3 signals used. There's the load up, which is shown in blue on this table. There's shed, which is shown in light purple, and there's critical peak, which is shown in dark purple. And so load up just means to increase energy use, heat more water, and store more energy in the water heater tank by heating water up to the user set point. The shed signal generally means to stop heating water unless there's a risk that the user will receive cold water. So for example, one way to do that is reduce the water heater set point to a lower value so it doesn't have to heat during that shed signal. And then the critical peak signal is like the shed signal, but it's just a more aggressive version of that. So it basically means to reduce demand more aggressively, for example, by reducing the set point to a lower value than the shed signal. So those are the different signals we use and the different amounts of time. So in our schedule during the warmer months, we use just a short load up for 1 hour because, there's not a lot of energy needed to heat up the water during the summer. And in the colder months, we used a longer load up period of a couple hours to allow more time for the heat pump water heater to heat the tank and store that water ahead of that peak period when the shed demand reductions would occur. And in the coldest months, we only use the shed signal, so that's the light purple. But in the rest of the year, we also used a critical peak, which is that more aggressive shed signal. And that's because we wanted to be able to target the reductions to the most important times of the day because the window was so big. And we understand by doing that, there might be some heating or recovery that happens during the other parts of the shed. But the most critical times of the day were targeted with that critical peak signal. And finally, for the duration of the study, we use this load shifting schedule to shift around the operation of the water heater about 75% of the time. And the rest of the time, the water heaters operated normally, and we used those normal operation days to collect baseline data. So that said, now I'm going to go over some of the results that we found in this study. So there's a lot of data here. The main thing is that participants successfully shifted up to 50% of their water heating electricity consumption out of the peak periods, which is great to see. But for some more detail on that, this slide shows the load shifting performance by season. So for those 4 different seasons I mentioned earlier, there are some obvious trends, like the colder it was, the more baseline energy use there was. So the colder it is, the more energy the hot water heater needs to heat the water. So therefore, because there's more baseline energy use, there's also more energy available to be shifted. Another aspect you'll see here is, like I mentioned, in the summer, we only did one long shed between 1 and 9 p.m. In the winter, we did a morning and an evening one. So there's a little bit of different results there. So given all that, the results were that the participants did shift their energy consumption out of the peak periods. They were able to shift about 30 to 45% of energy use in the morning, 25 to 50% of use in the evening, depending on the season. And the charts on the right show the baseline energy consumption in the light color, and the dark color is the amount of energy that was shifted out of the window. So the difference between the light bar and the dark bar is the remaining amount of energy they use. So they were able to shift a good amount of that out. As I mentioned, in the winter, we saw a lot more demand that was shifted because there's more baseline load available. So that makes sense. And another interesting finding is that there was a minor overall energy savings for these households of about an additional 5 to 10% from the load shifting. But this was a modest effect, and it wasn't a goal for the study to have additional energy savings, but it was something that we saw. And this slide shows similar information, but broken down by occupancy on if the home had 1, 2, or 3 or more occupants. The majority of households only had 1 occupant, but we found that the large households that had the higher hot water needs used more energy and therefore could shift more energy. So those larger households did have stronger results in terms of the actual amount of demand shifting. But both the low and the high occupancy households were able to shift a similar percentage of their baseline use. And in terms of cost savings, the electricity rates at the time we designed the study were quite low. So in the study, the off-peak rate was around 9 cents per kilowatt hour. So the cost savings were lower than they would be in a region with higher rates. We estimated an additional annual water heating electricity cost savings of around $45 from just the load shifting aspect. So that's about a 40% additional cost savings for these customers on top of the savings that they would get from the efficiency increase from getting the new hot water heater and switching away from their old standard electric water heater. So it is a, in terms of dollar value, because electricity is cheap in this area, it's small dollar value, but it is a significant increase on just that baseline savings that they have. And in the future, as rates increase and in other areas with higher rates, the cost savings would be more significant. And I'll just note that on the efficiency side, for this study, we estimated that the participants cut their water heater electricity consumption by about half due to the switch from electric resistance or standard electric water heaters to the new heat pump water heaters. And so here's some more results in terms of daily customer demand. So, that's the amount of power they're using throughout the day. So these profiles show the same information, but slightly different way of looking at it. So the load up periods when they're increasing the energy use and storing that energy, those are in blue. The critical shed periods are in red, and the normal shed periods are in pink. And so in terms of demand, what we saw were that the household water heaters, responded as expected. There was a minor increase in the load up period, and then there was the reduction that we talked about in the critical peak and the shed period. And so in terms of numbers, on average, the per household daily demand reduction ranged from about 35 watts in the hot summer when there's not a lot of demand to start with, to around 80 watts in the cold winter when there is more load to shed. So they were basically able to defer most of their heating loads to outside of the peak periods. And then we did find that after the peak period, the water heater would recover and reheat the water once that shed was done. But that recovery was generally in the range of using the heat pump on the water heater rather than using the backup electric resistance elements, which are less efficient, more expensive. And due to the prevalence of low occupancy households in this study, the baseline usage is generally low, but we were still able to show that they were able to shift the demand that they did have out of those peak periods while still providing the participants with hot water to meet their daily needs. So we didn't have really any kind of hot water issues related to the load shifting. There were some just related to other issues with the water heater, but in terms of the load shifting, that they were still able to get the hot water they needed. And just a couple more little details about using these heat pump water heaters for load shifting. So another aspect we looked at in this study was the prevalence of the operation of the heat pump water heaters backup electric resistance elements during the study. So these were all hybrid 240 volt heat pump water heaters. So they have electric resistance elements for heating as well as a heat pump. We didn't control the mode that the water heater operated in, as this was up to the participants, but they generally opted to operate their water heaters in hybrid mode, which can use the less efficient electric elements to heat water if needed, in addition to using the efficient heat pump most of the time. So in this slide, what we're looking at is the average electricity demand during those peak periods, and those align with our shift periods, as well as how often those electric resistance elements were operating, when we were load shifting versus when we weren't, to kind of see what the effect of this study was on that electric resistance element operation. So in the chart on the left, the total peak period demand on average is the total height of the bar. That's where the arrow is. The average demand while load shifting is the dark portion of the bar, the bottom, and the upper lighter portion of the bar is the average demand reduction due to load shifting. So that kind of highlighted upper portion is what we shifted out due to this study. And as mentioned, the largest reductions are going to be seen in the winter. And in the table on the right, it shows how often or how common it was for the electric elements to be used with and without load shifting. So what we found is that for these participants before the load shifting, the electric element usage was pretty low, not that common. It was about 3 to 5% of the time, depending on the season. So they were able to meet most of their hot water heating just using the heat pumps. But when we were doing the load shifting, it reduced how often those elements were operating by 30 to 60%, depending on the season. So it reduced that operation down to around 1.5 to 2% at most of the time. So this is another, benefit that we saw of the load shifting. But then looking more closely at what happened after the load shift windows when the water heaters were recovering all that heating, this slide shows the same information as the last slide, but the 1 hour immediately following the load shift window. And so in that hour, right after the load shift is occurring, there's a big jump in energy demand. So on the prior slide, we saw it was about 100 to 150 kW of operation during the peak windows. And right in this hour right after, it's around 350 to 400. Sorry, I think I said kW meant watts. It's around 350 to 400 watts in the hour right after. So there's a big jump in demand. And again, same thing on this slide. The total bar is the total demand. Um, the bottom portion is the baseline, and then the top portion is the increase due to the load shifting. So we did see that obviously because we are deferring heating for a long part of the day, and the hour after that is complete, that heating does recover. So again, the table on the right, we're looking at how often that electric resistance element was operating in that 1 hour after. So we did see that there was a little bit of an increase in the electric resistance element usage in the recovery window. So without load shifting, it was the elements were on about 4% of the time. And then when we were doing the load shifting, they were on about 12% of the time. So, it's still by no means a large portion of the time that the elements are operating, but it is something to be aware of and potentially control for in load shifting programs. So finally, I'm going to talk about the kind of last thing we looked at in this study. So we looked at a demand response event. And so, that's an event to reduce demand on the grid during a peak day. So we scheduled the demand response event to coincide with the coldest winter day in the study to simulate a grid peak day, because we wanted to demonstrate the ability of these water heaters to reduce demand on the grid to support the North Carolina grid during the system peak periods. So our test demand response event was conducted from 6 to 9 a.m. on January 17th, 2024, on a day where the temperature was about 20 degrees Fahrenheit. And for the demand response event, we used a 2-hour load up period followed by a 3-hour critical peak event. And that is a more aggressive strategy than we use on the regular cold winter days, because we wanted to see what the maximum amount of load reduction we could get from these units were on a grid peak day. So as shown in the graph here, the water heaters successfully reduced their demand to basically minimal or no operation during the event. That's shown in green. And they avoided the use of the heat pump compressors or the electric resistance elements for the duration of that demand response event. And there was an increase in the hour after the event, but hopefully that would be outside of the grid peak period. And compared to a baseline of similar cold days the same week, we found that the households were able to reduce their water heater electricity demand by about 72 watts per household, showing that these controlled heat pump water heaters can be a valuable grid asset to contribute to peak load reduction, even given their low baseline energy use. And I just want to talk about some of the kind of future opportunities in this region. So as I touched on earlier, the time of use rates we used in the study had these really long peak periods. So we were doing the load shifting for around 6 to 8 hours, depending on the season, which is a really long time, and it could be hard to do depending on a customer's hot water usage profile. In this case, we were able to do these long load shifts because the study households had low occupancy and low hot water usage in general. But for other households that have higher hot water demands, it might not be as easy to do. But since this study was completed, Duke Energy has come out with new time of use rates that have different season months, shorter peak periods, and also lower price discount periods. And these these new rates, especially with the shorter peak periods, could make load shifting easier for customers to do. And so we would expect that the performance of this load shifting would increase if we were to look at it using these new rates. The other thing is that these rates have these low price discount periods that are even lower price than the off-peak period. So if the customers are able to shift their energy usage to those periods, they could save even more than what we were able to find in this study. So this presents a really good opportunity in this region for the future for this kind of work to continue, but to have even stronger results. So I'm going to move on to some conclusions and recommendations. And, knowing that residential electric water heating is a significant contributor of peak electricity demand in North Carolina and in the Southeast, through this project, we showed that it was possible to shift a lot of that load off peak, which could result in notable peak load reduction at scale, which is great. And this load shifting is made possible by these newer heat pump water heaters that have these integrated connectivity features, and they can be used to provide some of these financial benefits for households, including low-income households and low occupancy households. And the financial benefits would be even greater for households with more usage or in areas with higher rates. So, in conclusion, some of the lessons we learned from this project were that connected heat pump water heaters can reduce electricity costs for households in the Southeast that have access to these time varying rates. They can reduce costs for low income households. And this technology can be leveraged to shift that electricity use off peak without any input from users on a day to day basis. And this technology can also reduce demand during the grid peak days, such as on cold winter days. It can be done without customer intervention, without causing cold water events, which is great. And an interesting finding was that the seniors in the low occupancy homes in this study with the low hot water usage were particularly flexible for load shifting. So this could point to future opportunities with other untapped demographics that haven't really been the main participants in prior kind of programs. And finally, we showed how engaging low income and hard to reach households can be successful when the programs are designed to respond to their needs. So we have some recommendations, some takeaways that we wanted to share from this study. We learned a lot about how to engage hard to reach customers and water heater load shifting or demand response programs. So these recommendations would help make future similar programs more accessible and relevant to all types of customers. And it would be a win-win scenario to have these devices contributing to grid needs while also providing cost savings for low income and energy burden customers, especially in the Southeast US where there's so much potential for this technology. So some of the recommendations for customers are to make sure they're educated on time of use rates and so they know how to minimize their costs by taking advantage of those. And then for installations, it's important to upsize the water heater units to ensure that there's enough hot water for especially multi-generational homes or homes that have variable occupancy, which is something we saw in this study. A lot of folks would have people moving in and out of their homes. For programs, an important lesson is to partner with trusted channels to reach hard to reach customers. So in this case, partnering with Preserving Home was so beneficial. Another recommendation is to target offerings based on customer demographics. So low hot water users, like the seniors in our study, might be more flexible. They could have a targeted offering, perhaps, or other demographics could have offerings targeted to them. And then finally, a really important finding was that it's really important to include enrollment and support options that don't require internet access or email. As Helen said, a lot of these participants were not comfortable with that or didn't have access to that. And so requiring those features does make it harder for many people to access these programs. And so in this project, we use a cellular communication module on the water heater. That was a good example of something that would fit the need of not requiring home Wi-Fi. In terms of rates, electricity rates that are favorable to load shifting incentivize better performance, but not all customer loads are flexible and can be shifted throughout the day. So one future concept we would recommend looking into is to explore using the connected product data, like the data that we got out of these water heaters, where it's available and where it's high quality enough to perhaps apply rates to only flexible loads so customers are able to participate where they can, but not be penalized for not being able to shift some of the non-flexible loads. And this is particularly important for low-income households. And finally, we found that our low-income customers that did have product issues needed support for both the equipment and the labor costs for any kind of warranty claim that they had. So it would be ideal if programs could cover extended labor warranties, for example, to ensure that low-income customers that have any issues don't have to take on the additional burden of repair costs. So, they might be able to get the new unit, but then they'll still have to pay for the labor for the install. So that's something that programs could target in the future. And yeah, that concludes the content we have to share. So thanks everyone for attending today. If you have further questions, you can contact us using the information here. And we also have a paper on this study published in the 2024 ACEEE Summer Study on Energy Efficiency in Buildings. So we can share that as well if anyone's interested. Thanks.
Thanks, Daniela. That was fantastic information and data that you shared. I would encourage y'all to drop the link to the study in the chat if you have it handy. In the meantime, for all of our participants on the line, I would encourage you to put any questions that you might have for Daniela or Helen in the Q&A box, or you're able to raise your hand, and if I can play with the tool, I will be able to unmute you, and you can speak with the whole group. In the meantime, I had a couple of questions that I would love to just get the conversation going. We were just curious to see, what would you all like to see as the continuation of this work? I'm going to start it pretty vague for now. So I can go to either Daniela or Helen or both.
Yeah, I can provide some thoughts here. So in terms of the continuation of this work, I would love to see as there's more uptake of heat pump water heaters in the Southeast, which provide great efficiency benefits for customers. Love to see some of those integrated features, connectivity features, be leveraged for future programs.
Helen, do you have anything to add?
No, I think that covers it. We're continuing to do work to better understand just the potential of load shifting with heat pump water heaters, on the more on like the policy side, and how to best inform codes and standards, and participating with AHRI committees related to that as well. So I think this project is a good way to point to, a demonstration.
Great. Yeah, and I know that this region, the Southeast, is a great place to do it because of our percentage of standard electric water heaters. But we're curious too to know whether this type of work y'all are aiming to do in other parts of the country, and what kinds of differences you might have to make to your approach to do so.
Yeah, definitely. So we are involved at Energy Solutions with similar programs in California, for example. There are some more robust programs offered where a lot of water heaters are enrolled in doing daily load shifting, and also looking at similar work in other parts of the country. And some of the differences we saw in the Southeast are just the climate is different. So having some of those colder winters and needing to just make sure that folks still had access to hot water when doing this during that important time period. Another thing particularly interesting in North Carolina is that some folks had their water heaters installed outside, or in other unconditioned spaces, and that's not as common in the other parts of the country. So just being able to manage, making sure that there was enough ability for the water heaters to heat while still, uh, um, you know, being able to do the load shifting. So it is something that we are very actively involved with in other parts of the country, but every part of the country is different and has its own idiosyncrasies and little unique things to deal with.
Mhm. Okay, I have one more question. Are these findings translating to conversations with utilities or government partners? How would you like to see this research used to encourage increased adoption? I guess that's two questions, but I see they complement each other.
I can start. Daniela would know more about existing utility program conversations, but we certainly do want to talk to any utility in the Southeast that's interested in learning more or hearing more details. Even just like heat pump water heaters in general and what the opportunity could look like. So yeah, the work that I do is more on the codes and standards side. So yeah, I'll let Daniela speak more to the program side.
Yeah, definitely. Yeah, so it's really important for studies like this one and the other work, the prior work, such as the prior P&L studies, to show and demonstrate what is possible, and also to help pinpoint some of the issues uh, early on, like some of the kind of communication challenges, connectivity, best practices, et cetera, that need to be worked out before scaling this to a larger program. And so we find that a lot of partners that are interested in this kind of thing have a lot of questions around, how those connectivity, communication, et cetera, how that could work. And so this work has been very useful in providing some information on that, as well as the other work that we're doing. And in terms of, how this research could be used to increase adoption, something that Helen mentioned that is useful is working with on the sort of codes and standards side as well to standardize some of these features, make sure everything talks to each other out of the box, make sure that there's everything's working and can really deliver the grid benefit. So that's one of the ways that this research is being used to support increased adoption, so that hopefully in the future, we've got all of the kind of issues worked out, and these products are ready to go and provide those benefits.
Right? We did just have a question come in, so I'll read it off. Can you share more about what loading up meant for the water heater if the temp was kept constant? And what's the latest finding from this or other studies regarding the benefits and any challenges with mixing valves?
Yeah. Yeah. Yeah, that's a good question. So for this study, because we didn't install the water heaters, that was done by Preserving Home. They were not installed with mixing valves, and so we weren't able to do what is called the advanced load up, which is heating the water like above the set point to store more energy. We were able to just do the basic load up. And so what the load up does is that, the water heaters have a certain dead band where, they'll start and stop heating water um, around the set point. So that the load up just makes it so that it will heat the water up to that set point, even if it's not quite at that point where it would normally start heating. And it just makes sure that the tank is kept at that set point temperature in advance of that shed event. So, but it is a pretty modest effect compared to if we were able to heat water above the set point, if there was a mixing valve. So to the second part of your question, if there's a mixing valve, there's so much benefit that actually provides much more value, because then you can heat water above the set point, store more energy, and get through that shed period without as much of a recovery after. So in the future, for these types of products where it is possible to install a mixing valve, that's definitely a benefit.
Great question. Okay. Looks like we don't have any other questions coming in. In the meantime, please Feel free to reach out to Daniela, Helen, and Claire. Thank you so much for your time today and for presenting on your study. It's really interesting and exciting to see this work being done in North Carolina in the Southeast. Also, I'm going to make the plug again, attend the Southeast Energy Summit. I linked it in the chat. There will be more conversations around these types of technologies happening there. Also, as a reminder, this webinar was recorded today. That will be sent out with the contact information and any resources listed in the chat. So yeah, thank you so much for joining us. If there's any other questions, please feel free to follow up with our speakers after. Thank you to our speakers today for their time.
Thank you for having us.
Yeah.
Yeah, thank you.
Thank you.